Good morning, everyone. Today we're going to take a look at unmanned systems. You're going to be doing a bit of a research project on this, so I figure I'd give you a little bit of background information about sort of what this is all about. Um, so when we talk about aircraft and vehicles in general, we look at the human element and we realize that, of course, as humans, there are quite a few things that limit our abilities to perform a mission. So this slide is really sort of just asking questions about, what are the limitations that affect human operated systems. So when you consider, NASA astronauts or say aircraft that are used in the military, spy planes is a great example because, of course, spying can take a really long time sometimes. What are the limitations, right? Well, how many hours can you stay awake for consecutively? Most of us operate on 12 to 18-hour days. How long can you go without eating or drinking, right? How far can you see? How long can you stay sitting in a tight space? How well can you see at night? How long can you survive in the vacuum of space? And how long can you survive in microgravity? So these are all questions that Boeing and Lockheed Martin and NASA and other companies have to deal with all the time when it comes to trying to understand, how humans can operate in under what conditions. And so even the best military pilots and most well-trained astronauts are going to struggle and have these limitations. So this brings to the forefront the idea of unmanned systems and that sort of the inherent advantages that an unmanned system can offer. So, and of course, yeah, this final question here: what is the value of human life? Obviously, we don't want to lose human life, and so this cannot be overstated. The idea of an unmanned system can really ultimately, prevent human lives from being put in harm's way, and so that can go a long way to protecting us. So, a system without a human on board, the human factor obviously is going to be reduced. Okay, but that requires a lot of technology, right? In order to replace well, first of all, you can't truly replace the human brain on board, right? That's an impossibility at this point because our computer systems don't have sufficient AI to truly replicate what a human is capable of. But that said, if you know exactly what your system is going to do in a very routine and rigid way, then yeah, you can replace the hands and motor controls and sort of just routine rote operations that a human could do. You can't replace their decision making, you can't replace their critical thinking, but you can replace sort of just the mundane activities of a human, and that's what unmanned systems really look to do. Okay, so these are just a few examples. Obviously we have three categories that we're looking at. We're aerospace, but we're not only looking at air vehicles, we're also looking at ground vehicles and maritime vehicles. And I would extend this into, of course, space vehicles as well. I'm not exactly sure why they didn't include that, but I do have a video that gives you an idea of some good examples for unmanned spacecraft. But that's very common. Unmanned spacecraft is much more common than manned spacecraft. So we have many, many unmanned satellites. We have many probes, many missions to other planets. In fact, every mission to another planet has been unmanned. We've never been anywhere but Earth and the Moon. So in any case, yeah, if we have air, we call those UAVs, which we've looked at in the past. UGVs or ground vehicles, and UMVs, I'm sorry, UMS. Those would be, water systems. So, submarines or any underwater or even above water boats and watercraft. So, when it comes to the design components, in other words, you're a designer, an engineer, and you want to consider what is important when you're trying to create a vehicle. Yeah, operational environment and task. What do you want to do, and what is the environment in which you need to do it? That's the most important question. Sensing is very important because if your craft is going to operate in an environment and it's going to do so autonomously, then its best bet is to gather information from its environment. So sensing is very, very important in order for it to, quote, make decisions in other words, respond to its environment. And that's where the information processing comes in. So you could put communication in there in two different ways. Communication could be between the sensors and the processors of the unmanned system, but the communication could also be relaying data back to the human system. So it could be sending, for example, you could have a space probe sending data back to NASA. So that communication can go either internal or externally. But certainly you need information processing. And then critically, you need an energy source and energy transfer as well. So energy source is simple enough for us, right? That we're talking about fuel or a battery, whatever it might be. And an energy transfer depends upon the circumstance, but it's generally related to how that vehicle interacts with its environment. But we're going to talk more about that. Okay, so unmanned systems, new age or old? Well, this is sort of a bit of a history, right? So in 1888, Louis Brennan demonstrated a wire-guided torpedo. In 1898, Nikola Tesla introduced the teleautomaton, a 4-foot-long boat that could start, stop, and turn using radio frequencies. This is actually kind of funny. You can read stories about this, where he had this little boat in a fountain, and he convinced people that they were controlling the boat with their speech. And so they would tell the boat to do something, and the boat would like turn and obey their commands. But really, what was happening is there was a remote control, which of course was brand new and nobody knew about because Tesla was using radio control for the first time. And so he would simply listen to their commands and then turn the boat the way they told him to do it. And so they were none the wiser. So he convinced people that the boat was listening to their commands, but in reality, he was just using, of course, a radio-controlled device. Why was the first unmanned system a maritime system? Naval warfare was actually a pretty significant focus for the military strategists at the time. So right around the turn of the 20th century, around the turn of the 20th century, the Navy was really trying to expand their capabilities, and they were trying to investigate what are the options for unmanned vehicles to get an edge in warfare. So that was one of the reasons why there was a lot of research in that, and ended up, of course, coming into tremendous use in World War I and World War II. So, yeah. All right. So, what concepts did Tesla need to understand in order to create his unmanned maritime system? So, yeah, as we said, this is the design process. So, the operational environmental task, right? Operational environment and task, excuse me. And so, yeah, obviously you have a water system, so buoyancy is very important, understanding Archimedes' principle, which we studied in physics. Materials, because if you're going to have particularly a craft in salt water, then there are, material limitations and corrosion and maintenance and things like that you have to consider. And of course, the structures themselves. In other words, how are you going to piece these things together? What is an appropriate structure for such a device? And there's many different approaches you can take, of course. You have to understand physics as well. So not only the buoyancy, but you have to understand inertia, and you have to understand how this object is going to respond to these commands. You had to have an energy source. So Tesla, for him, it was a battery. So his boat had a battery attached to it, and that was his source. But again, around the turn of the 20th century, this is still pretty new stuff. People didn't even fully understand this. The average person didn't. Energy transfer, right? So you have to have a way to get that energy from the battery into motion, right? So this is what we call a motor typically, right? Electrical motor, some sort of transfer energy from the motor from the battery to the actual device that's going to cause your unmanned system to move. So you have to have that energy source, and then you have to have that energy transfer, which, as I said before, interacts with the environment, right? So in this case, the propeller is going to transfer energy from the battery to the motor, and ultimately, through the motor, via the motor, ultimately to the environment, which is going to allow, say, the boat to push the water, and then the water pushes the boat. So that energy source and energy transfer are critical. Communication, in the case of this Tesla example, was the radio frequency. So we had a communication between the device that controlled the boat and the boat itself, and so he was using electromagnetic radiation. So this is still pretty much how we communicate with all systems around the world. We're generally using radio waves. Anytime you're making a phone call, you're using radio waves. Anytime that you are uh, well, I mean, it's everything. It's television signals. It's any interactions with satellites, GPS. This is all on the electromagnetic spectrum. So that hasn't really changed a bit. And then, of course, information processing. So there were very primitive, if you will, mechanical. I hesitate to call them this mechanical computers, but really, what you needed is a way to transfer information about communication into commands on the boat, and that was probably one of the most I would say difficult hurdles for Tesla to overcome because, again, they did not have computers. Computers were still another 50, 60 years away. And so Tesla had, as I suppose, what could be referred to as a very crude mechanical computer that allowed his boat to transfer an incoming radio signal into a command for the motor. So when was this first unmanned aircraft was actually designed in 1915. This is remarkably soon after, of course, the Wright brothers flew. So that's a very short period of time. But of course, as you can imagine, with an unmanned aircraft system being designed so shortly after flight, there were very many limitations, right? So what were some of the components that limited the success? Well, pretty much everything, right? So there was so little technology around the time. These were not advanced aircraft systems, okay? So what were the operational environment and task limitations, right? Well, flight concepts weren't very well understood. Automatic stabilization didn't really exist. It was still, remember when we talk about automatic stabilization, we're talking about designing the aircraft in such a way so that it has positive stabilization. In other words, it's a very stable craft, so it's not as maneuverable. It'll automatically head back towards its equilibrium point. Autonomous navigation didn't exist at all, so at best you're radio controlling something, and then of course you're going to lose range for that shortly after. So it was very limited. Today, with autonomous navigation, you don't have to worry about radio control. You can, of course, still do this with drones and stuff. You can control them via radio, but we, of course, know there are autonomous drones. We understand many of the flight concepts, and so we have a very robust theory around that, and we have automatic stabilization. That's not a problem. So what energy source limitations existed? Well, electrical batteries were very primitive. We, of course, were still using, petroleum fuel. One thing to note, both of those were very heavy at the time. Less fuel efficient motors. And of course, batteries were very primitive. So very heavy, very limited fuel source, so that's not going to be good for flying. And what energy transfer limitations existed? So as it says here, pneumatic parts from organs, we're talking about, the piano type church organ. Those were used for mechanical parts. They were very high weight, low power engines. Again, very inefficient. So energy transfer to from the energy source to the environment was very low. And of course, today we've made tremendous strides in terms of motor efficiencies and in terms of battery and power sources. Communication, radio frequency transmission and receiving, that actually hasn't changed a whole lot, as I said. So this top one here, radio frequency transmission and receiving, is more or less unchanged. Basically what we've done there is we've just gotten better and we've gotten longer range communications possible. But fundamentally that technology has remained the same. And then what information processing limitations existed? Well, tremendous information. It pretty much had to be done by the person operating. There were no computers. Okay, so today, of course, we have computers, and we have very cheap, very powerful processors that occupy very little space. In the early days of computers, you've probably heard that computers used to take up entire rooms. the Turing machine and things like that. So they were very sort of mechanical systems. And what we've done is we miniaturized those switches to down to this nanoscale. Now we're talking about on the 9 and 12 nanometer processing scales. So yeah, obviously huge advancements in information processing. That's where it's changed the most. So yeah, today's unmanned systems, they're very versatile, adaptable, and persistent, right? So they're used for all sorts of different applications, civil and commercial. Of course, we now have Amazon delivering packages via drones and other companies as well. Reconnaissance and combat. Yeah, I mean, we have spy drones, we have attack drones. I don't need to tell you guys this, you've seen it in the news. Logistics, I don't know, UPS, right? But certainly solving all sorts of problems and doing all sorts of mundane tasks. Research and development, target and decoy, exploration. That last one's, of course, a big one when it comes to two frontiers, I should say, of exploration, and that would be not only space, which is obvious, but also the deep depths of the ocean, where you really can't put people very much. We've had, a handful of people down at the bottom of the ocean. There have been more people at the bottom of the ocean. I'm sorry, fewer people at the deepest part of the ocean than there have been in space. So, yeah, we still have a lot of exploration to do, high and low. So that is the end of the presentation, and I want to take the last couple of minutes here to just introduce you to the assignment you're going to be doing. Now, this is what you'll see when you go to the Project Lead the Way website, Unmanned Systems Investigation 4.2.1. This originally called for teams, and if we had done this in the classroom, we probably would have worked in pairs. I considered this, but I am concerned about people's work schedules and people's workload and coordinating all of that. I don't feel like if you worked in a team, it would reduce the workload on you guys at all. And so, honestly, in consideration of your schedules and the difficulties you might have in working as a team and communicating, I elected to simply have this be done as individuals, which I think makes it easier in the long run. So, sorry if that disappoints you in any way, but I adapted this assignment for individuals to complete. So, if you go to the web page here, you're going to see a different set of instructions that you're going to see on Shobi, because this is assuming teams, and the one on Shobi is assuming you're working as an individual. So just keep that in mind. But in short, you're going to be doing a research project and presentation. This is a formative assessment, so it doesn't have to be something that you take 10 hours to complete. But yeah, essentially what you want to do is you're gonna research two unmanned systems, and you're gonna be answering a series of questions about those unmanned systems. You're gonna after you've investigated both of them, you're going to pick which one between the two that you like the most, and then you're going to create a presentation on that. You can do a video, you can do Google Slides, there are other options, but whatever you prefer and you find easiest or most stimulating to complete, you are welcome to do. But all this information is on Shobi, of course, and that's where you should go. Don't bother with the Project Lead the Way website, because as I said, it is set up for teams, and I'm going to have you guys work individually. And then there is this rubric, and this is also on Shobi, so you'll see this exact photo on Shobi for your rubric, and this comes from Project Lead the Way as well. So essentially, you're going to be graded on these four categories on a 5-point scale. And so I would just ask that you do your best to read this and make sure you understand what the expectations are, and to create a good presentation. So if you have questions, of course, you know how to get in touch with me via email and via Google Hangouts. I am going to give you time for this. Currently, I am having this due on Monday. So this is similar to our schedule last week, where I gave you this parachute assignment, and then you had several days and the weekend to work on it. Same kind of thing here. Now, I know that Sunday is Easter, so I obviously wouldn't recommend waiting for very long. I would encourage you to work on this today, Tuesday, tomorrow, Wednesday, and then on Thursday. Friday, Saturday, that's up to you. I don't know if it shouldn't take you that long. If you put in 2 or 3 days work on this, you should be done with it. So I'm kind of giving you a larger window than is necessary because of Easter, so keep that in mind. And yeah, that's just our references, okay? So I'm going to go and post this, guys. If you have questions, hit me up, and I hope you have a lovely day.